Okay, hello everyone. Let's move on to hypothesis testing part 2. Section 10.4 is calculating type 2 error probabilities and finding the sample size for a z-test. We hope that our test have enough power. We hope that our test have a small type 2 error rate. So to do that, we need enough number of sample size. This is why we need to consider the type 2 error probabilities, and we need to find the sample size for z-test to get enough power, which is 1 minus beta. Uh, so let's consider this situation. For the hypothesis H0 is theta equals theta 0 versus an HA alternative hypothesis is theta is greater than theta 0. Then under the null hypothesis, under the H is, let's say this in this example, H0 is mu equals 90, and under this null assumption, our the distribution of mu hat would follow y bar. Under this assumption, y bar would follow normal distribution like this. And also under alternative hypothesis, or if HA, if mu equals about 98, then under the H alternative, the distribution would be something like this, and so we can calculate type 1 error and type 2 error. So type 1 error alpha would be the probability of rejecting H0 given H0 is true. So given H0 is true, the true distribution is this blue distribution, and rejecting H0 implies that the rejection region would be this part. Rejection region is this part, so this is the area here. So this blue area is alpha. And what about beta, the type 2 error? Type 2 error is probability of do not reject H0 given H alternative is true. So here H alternative is mu equals 98. So given mu equals 98, so this red distribution is alternative hypothesis. And given this red distribution, do not reject H0 means that this red part do not reject H0. So rejection area is this area. So do not rejecting H0 is here. So beta is area here. So beta is this red area, and you can calculate this with this. Okay, and to calculate this, we know that this one, theta hat minus theta alternative divided by sigma theta hat. This one is z, and this is this red distribution, and this value is z beta, and you can calculate beta this way. Okay, and let's move on to a simple example, and we will derive how we can get the sample size n. Actually, the way is using this point. Okay, I will explain it from the next slide. Okay, let's move on to example 10.8. Suppose that the vice president in example 10.5 wants to be able to detect a difference equal to 1 call in the mean number of customer calls per week. Uh, that is, he wishes to test this hypothesis with the data as given in example 10.5. Find beta for this test. Okay, so for the situation, the step one is specifying hypothesis and level alpha. So this is our hypothesis and alpha is 0.05 from here. And the second step is finding test statistic. And the test statistic Z would be y bar minus mu 0 divided by standard error of y bar. And this would follow normal distribution. And the rejection region would be our Z is greater than or equal to Z alpha, and here Z alpha is 1.645. And okay, that's it. And actually the situation is something like this. And we want our alpha, the probability of this thing is alpha. And to calculate beta, we would like to find the probability of this distribution is less than this k. So we need to calculate this k. And since the axis is with respect to y bar, we should find the rejection region with respect to y bar. So this is our z is y bar minus mu 0 is 15, and the standard error is 9 over 36, and this is greater than or equal to 1.645. And if you calculate this with respect to y bar, you can calculate that y bar is greater than or equal to 15.8225. So the k, our k here is 15.8225. Okay, so we calculated our k, and the next step is calculating beta. Beta is probability of do not reject H0 under H alternative is true. And so if H alternative is true, the distribution would be this thing. And do not rejecting this one would be the probability of y bar is less than or equal to k. So we want to calculate this probability, which is probability of y bar is less than or equal to k. And here the distribution here is H alternative is true. So this time we should normalize it with respect to alternative hypothesis. So it becomes probability of y bar minus mu alternative, which is 16, divided by the standard error is 9 over 36, and this is less than k minus 16 divided by square root of 9 over 36. Okay, and yeah, that's it. And actually, we know that k is 15.8225, so we can calculate this number. And so um, if you calculate this number, actually this one is follows normal distribution, and if you put a k as 15.8225 here, then you can calculate this value using calculator, which is minus 0.36, and using using R, you can find this probability, and this is 0.3594. Okay, so this is how you can calculate the value for beta. What else? And actually, so this is our answer. This is our answer for beta, and actually this is we can call it z beta, and by using the formula, this is z beta. From here, actually, the error rate beta is a bit large, 0.35. We have a large amount of type 2 error rate. So sometimes we want to have small alpha and small beta. So we want to have alpha equals 0.05, and we want to have beta equals 0.05 as well. Then how can we calculate the sample size to have beta is 0.05? And actually, as you can see that this one is function of a sample size. There is some function of sample size n. So if you so in the formula, actually for this k, this is something like mu zero plus z alpha times standard error of y bar. This is k. This is k under the null hypothesis, and this k is mu alternative minus z beta times standard error of y bar. Okay, so this is k. So this k is this thing, and if you set up alpha and beta, these two values are known, and this one depend on sample size n. So in this equation, the only unknown parameter is n. So you can calculate sample size n using this formula. I will tell you more details in next slide. Here, I'd like to describe how you can calculate the sample size, finding the sample size for z-test. So, from the previous example, if you want to set fixed alpha and fixed beta, so previously with fixed alpha and with fixed sample size, you calculated beta. However, if you want to certain level of alpha and beta, so this time alpha and beta are fixed, and the n sample size is unknown, then how we can find the sample size n? So just like before, the mu zero plus z alpha times standard error, this is k, is equal to from alternative distribution side, mu alpha minus z beta times standard error. They are the same. These are k. They are the same. So you can solve it with respect to n, and you can derive this equation. for sample size for an uptail alpha level test, you can decide the sample size n using this formula. And actually, for many of cases, you can think about this formula and you can derive n for any general case. For any, sometimes mu 0 is about y bar, or sometimes it is about p hat, sometimes it is about y1 bar minus y2 bar, and sometimes it's p1 hat minus p2 hat. For any situations, you draw the graph and think about this kind of equation, then you can derive the equation for sample size n. Okay. Previously, I solved it for a one-tailed case. However, for two-tailed case, the alpha here is alpha over 2. So this area is alpha over 2. If this part is theta 0, then this k is theta 0 plus z alpha over 2 times standard error of theta hat. So this k is this thing, and from the alternative distribution side, under H alternative, theta 1 or theta A, theta alternative minus z beta times standard error of theta hat, this is k. So you set up this equation and solve it with respect to n, then you can find the formula for sample size n for two-tailed case. Actually, this is just putting z alpha over 2 rather than z alpha in the previous formula. Let's move on to example 10.9. Suppose that the vice president of example 10.5 wants to test the H0 is mu equals 15 against H alternative is mu equals 16 with alpha beta equals 0.05. So this time we want to have fixed type 1 and type 2 error, and we want to find the sample size. That's the problem in this question. And from the situation is like this, and from here we would like to use the information of alpha and beta. So what is alpha? Alpha is probability of actually z is greater than z alpha under H0 when H0 is true. So this is actually probability of, and Z alpha is Z 0.05, and this is from the previous calculation, it's 1.645. And and actually you can calculate this from using R, Q norm 1 minus alpha, then you can get this value. Okay, and from here our z under null hypothesis, our z is y bar minus 15 divided by square root of sigma squared is 9 over n. Okay, and this is greater than or equal to 1.645. And and this is probability of y bar is greater than or equal to 15 plus 1.645 times 3 over square root of n. Okay, so this is our alpha, and what is beta? And beta is probability of z is less than or equal to minus z alpha given H alternative. And here, the alternative mean is 16. So this time, the probability, it is probability of y bar minus 16 over 9 over n, and this is is less than or equal to minus 1.645, and this is probability of y bar is less than or equal to 16 minus 1.645 times square root of 9 over n. Okay, so um, this is our k. This is our k. And so we make them as same value. So our equation would be 15 plus 1.645 times 3 over square root of n equals 16 minus 1.645 times 3 over square root of n. And actually, this equation can actually, this is from here. And so from here, to let you understand the situation, I derived this directly. But if you understand this situation, you can directly use this one. And then solve it with respect to n. Then you can calculate n. So let's finish our proof. So 1 equals 2 times 1.645 divided by square root of n. So n is 2 times 1.645 squared. And this value is about 97.4, about 97.4, and so our n is 98. So this is our solution for n. And the important thing to remember is for the fixed alpha and beta, you calculate this. So if you don't remember the formula, use these hypotheses and 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 um, understand this formula, then you will eventually get the sample size n, or remember this equation and solve it with respect to n. Then you can also find the sample size n. Okay. Uh, Okay, let's move on to exercise problem 10.40. Refer to exercise 10.33. The political researcher should have designed a test for which beta is tolerably low when P1 exceeds P2. When P1 exceeds P2 by a meaningful amount. For example, find the common sample size n for a test with alpha is 0.05 and beta is less than 0.2 when in fact P1 exceeds P2 by 0.1. Here our hypothesis is that H0 is P1 equals P2, and H alternative is P1 is greater than P2, and actually P1 minus P2 is 0.1. We want to calculate beta for this case. Okay, and and actually we can derive like this. We can derive probability of z is less than or equal to larger than z is larger than z alpha is alpha under H0, and we can also calculate probability of z is less than z beta equals beta here under H1, and uh, and also here the z is P1 hat minus P2 hat minus P1 minus P2, the difference of these two, divide by standard error of P1 hat minus P2 hat. This is the related distribution, and this should follow normal 0, 1, and this part is square root of P1 1 minus P1 divided by N1 plus P2 1 minus P2 divided by N2. So this is our standard error. And you can solve these with respect to P1 hat minus P2 hat, and then actually you can find you can again derive this equation. So here theta 0 is P1 minus P2, P1 minus P2. P1 hat minus P2 hat, and this one is exceed by this thing. So actually this is P1 not P1 minus. So this is under H0. This is P1 minus P2. This is under H alternative P1 minus P2. So this is 0 plus z alpha. Alpha is 0.05, so 1.64645, and this one is this thing, and equals this is 0.1 minus z beta. Z beta is z 0.2, which is 0.84, which is about 0.84, and again sigma theta hat. And for the conservative this one, here the maximum value of this thing is when P1 and 1 minus P1 is equivalent. So for P1 times 1 minus P1, the formula is something like this. This is P1, and y-axis is P1 times 1 minus P1, and maximum is derived when P1 is 0.5. So the maximum of this thing is 0.25, and when P1 is 0.5. So for the conservative case, the variance estimate, we put P as 0.5, and so here, and also we also assume the same number for the first population and second population. So we will use an N for N1 and N2, and so this is square root of N 2 times 0.5 times 0.5. Okay, and so we will put this thing inside of sigma of theta hat, sigma theta hat. Okay, and now put this inside of here. So 1.645 times and actually this is 1.645 times plus 0.84. Here square root of 2 times 0.25 divided by n equals 0.1. And you can solve it with respect to n. then you will get n equals 308.76, and so our n should be 309. So this is our answer for this question. And from here, actually, um, we use the maximum value of this thing. Probably some of you may wonder that why we need to use the maximum value of this. And actually, this is if we have larger value of this, then our n should be getting larger. So we will have so we want to have our n conservatively. So we need to maximize this part so that we can have our n in the conservative manner. So that's why we put p as 0.5. So sometimes in the problem they give you the p parameter under the null situation and under the alternative situation. Sometimes the problem gives you the number. In that case, you can put that number when you are solving the problem. However, if there are no hint for the P1 and P2, you can put 0.5 for P. For the conservative case, and you need to derive your sample size n using that quantity, and this is how you derive with that number. Okay. And homework for chapter 10.4 are these. Okay, so we have learned how to calculate the sample size based on the type 1 error and type 2 error fixed. And so this is end of the chapter today, and in next week we will going to have our midterm exam. So see you after the midterm, and thank you.